Did you know plucking half a string produces a note an octave higher than the unpressed string? Plucking 2/3 of a string produces a note a fifth higher than the unpressed string, and plucking 3/4 of a string produces a note a fourth higher than the unpressed string. These are just some of the discoveries made by Pythagoras. Pythagoras was born around 570 BC in ancient Greece. Through his teachings and beliefs, as well as being an incredible mathematician, he gained a lot of followers. Pythagoreans believed that numbers were the ultimate reality governing music, geometry, and cosmology. It is very likely that you studied and used Pythagoras' theorem in maths at school, which involves the relationship between three sides of a right-angled triangle, a squared plus b squared equals c squared. But Pythagoras' mathematical work in music was also very important. He discovered that musical notes and consonant harmonies are produced by simple integer-based mathematical ratios. This is a public domain image of the design of a monochord. Tradition believes that Pythagoras discovered these mathematical ratios using a monochord, which is a single-stringed instrument with a movable bridge. By moving the bridge into different positions, Pythagoras realised that the ratio of the full string length to the shortened string length when the bridge was moved produces notes of varying pitches. From this discovery, he now knew that if he wanted to create an octave above a fundamental note of C, he would need half the length of the original string. And if he wanted to create the note G a fifth higher from the fundamental note of C, he would need to use 2/3 of the length of the original string. He also knew that if he wanted to create the note F a fourth higher from the fundamental note of C, he would need to use 3/4 of the length of the original string. So how did Pythagoras calculate these ratios? Let's begin with the ratio of an octave. Pythagoras started off with a string tuned at middle C. He realised that if he stopped the string at the halfway point, the note produced would be a high C, an octave above middle C. This would be the same as cutting the string to half the original length. The ratio of the strings is 2:1. The whole string length measures 2 halves and the shorter string length measures 1 half. Therefore, the ratio of the whole string length to the shorter string length is 2:1. The frequency vibrations are inversely proportional to the length. The shorter string vibrates 2 times for every 1 time of the whole string length. Now let's move on to the ratio of a fifth. Pythagoras started off with a string tuned at middle C. He realised that if he stopped the string at 2/3 of the length, the resulting note would be G, 1/5 higher than middle C. This would be the same as cutting the string to 2/3 of the length. The resulting ratio is 3:2. The whole string measures 3/3 and the shorter string measures 2/3. Therefore, the ratio of the whole string to the shorter string is 3:2. The frequency vibrations are inversely proportional to the length. And now let's look at the ratio of a fourth. Pythagoras started with a string tuned to middle C. He realised that if he stopped the string at 3/4 of the length, the resulting note would be F, 1/4 above middle C. This would be the same as cutting the string to 3/4 of the length. The resulting ratio is 4:3. The whole string measures 4/4 and the shorter string measures 3/4. Therefore, the ratio of the whole string to the shorter string is 4:3. The frequency vibrations are inversely proportional to the length. It was time for Pythagoras to put his master plan into action. Now Pythagoras knew the ratios he needed to play an octave, fourth and fifth. Being a master mathematician, he knew that he could calculate the lengths of strings needed to play all the other intervals in a scale. So taking a scale of C, also called the Ionian mode, he set to work. So, how was he going to find the ratios needed to produce the intervals of the second, third, sixth and seventh? Pythagoras believed the fourth, fifth and octave intervals he had calculated were pure and entirely consonant. In other words, they sound beautiful when C and F, C and G, and C and an octave higher are played together. It will probably come as no surprise that these are the intervals we now call perfect, the perfect fourth, perfect fifth and perfect octave. His plan was to choose one of these intervals and use it to calculate the intervals required to produce the other scale notes he needed. He believed the purest of all intervals was the octave. However, using this interval to create any other interval wouldn't work, as it would only leave him with other octave notes, not the notes he required. He felt the next purest interval was the fifth, and he believed he could use this to create all the intervals he needed. So he set to work. Now, I'm sure one thing related to the interval of a fifth has already sprung into your mind, and that is the circle of fifths. We use this tool to analyse music, to create music or to transpose music. If you want to learn more about it, you can watch my detailed video on the circle of fifths, which is on my YouTube channel. What we must remember though is the circle of fifths as we know it is related to keys in music, for example G major, B flat major, F sharp major and so on. When Pythagoras calculated the ratios required to create different intervals that would produce the notes he needed, he used a very similar system, but with a different intended outcome. It's important we don't confuse the two. Remember, in this video we are talking about calculating intervals required to produce notes on a scale. So let's talk briefly about what exactly this fifth interval is, and how Pythagoras was going to use it to complete his task. This is the circle of fifths. It is called the circle of fifths because each key is a fifth apart on the diagram. The interval of a fifth contains 7 semitones. If we start at C and move 7 semitones to the right, we end up at G. The key of G has a sharp in its key signature, which is F sharp. For keys containing sharps, we always move to the right. If we then continue to move in fifth intervals to the right, we arrive at all the other major keys containing sharps, which are D, A, E, B and F sharp. The diagram shows the beginning of this pattern, moving from C to G to D to A. If you start at C and move in 7 semitone intervals or fifths around to the left, you arrive at all the major keys containing flats, which are F, B flat, E flat, A flat, D flat and G flat. The diagram shows the beginning of this pattern, moving from C to F to B flat and to E flat. Watch how all the keys are added to the circle of fifths. Keys with sharps around to the right and keys with flats around to the left. As you will remember, Pythagoras thought he would use his interval of a pure fifth to calculate the other intervals needed to produce each note on the scale. He believed that if he stacked fifths on top of each other, he could work out the ratio needed to create the interval required to produce every note needed on a diatonic scale or mode. Pythagoreans did not play scales as we know them today, such as D major and B flat major. Instead, Pythagoras used modes based in C major. If Pythagoras worked out the ratios needed to produce the intervals required to create the notes in the Ionian mode, also known as C major, he could play every other mode by starting on a different note of the C major scale. Take a look. This is the Ionian mode, otherwise known as the scale of C major. The following modes contain the same notes as the Ionian mode, but just start on a different note. So the Lydian mode starts on the note of F, and the Phrygian mode starts on the note of E. Looking at the circle of fifths on the left, it seems we would just move round to the right to find the ratios required for intervals needed to produce the note G, D, A, E and B, and then move left to work out the ratio required for the interval needed to produce the note of F. We could ignore everything else, like this. Done. End of video. Well, not quite. Let's take a look at the issue that arises. Let's take the Ionian mode and compare it with the Lydian mode. If we go from note 1 to note 4 in the Ionian mode, it makes the interval of a perfect fourth. But if we go from note 1 to note 4 in the Lydian mode, it makes an interval of an augmented fourth. So we need to know how to create all intervals, not just intervals, to produce the Ionian mode, or as we know it, the scale of C major. So try to think of each note on the scale as an interval from the fundamental note of C. Try to think of the note B as a major seventh from C rather than the note B. Or try to think of the note E as a major third from C rather than the note E. This way we can apply the intervals we calculate from any starting note to create any of the modes. But was the idea of creating a scale a new thing? Absolutely not. It is thought that from at least 1800 BC, the Mesopotamians used a 7-note scale that is the ancestor of our modern major scale. So although Pythagoras didn't invent the musical scale, it is thought that he was the first to find a logic behind the notes, and of course this lay in mathematics. And he must have done a good job because Pythagorean tuning, which is the exact note created from each of his interval ratios, lasted for another 2000 years after his death. So let's find out how he did it. It's time to see how Pythagoras combined mathematics with music to pile fifths onto fifths to form every interval required to play any mode. We are going to use a fundamental note of C to form our chromatic scale, but later in the video we will use our interval ratios to form every other mode available to Pythagoras. So let's start by adding our fundamental ratio, which is 1 to 1. We have already seen that the octave interval has a ratio of 2 to 1, so let's add that too. Let's simplify these ratios to 1 and 2. We're going to start by calculating the string ratios on the right of C. We're going to start moving in fifths from C. We have already calculated that the note G is 1/5 higher than C and has a string ratio of 3 to 2, so let's add that to our table. OK, it's time to pile our first fifth on, which takes us to the note D. To calculate the string ratio needed to produce the interval which leads to the note D, we need to take the ratio of the previous note of G and multiply it by the ratio of a pure fifth, which is 3/2. This gives us an interval fraction of 9/4. This is where we run into a problem. All of our string ratios need to lie in between the unison and the octave, and therefore in between the numbers 1 and 2. When we convert the improper fraction into a mixed number, we get 2 1/4, which is obviously greater than 2. As a decimal, this would be 2.25. This is because we started at the fundamental of C. The first pure fifth took us to G, and the second pure fifth has taken us to D, but into the second octave. To bring the note D down an octave so its ratio lies between 1 and 2, we need to divide by 2. This gives us a final interval fraction of 9/8, or a ratio of 9 to 8. This is the interval ratio of a major second. Let's add this one to the table. It's time to pile on our next fifth. To calculate the string ratio needed to produce the interval which leads to the note A, we need to take the ratio of the previous note of D and multiply it by the ratio of a pure fifth, which is 3/2. This gives us an interval fraction of 27/16. We have also just found the interval ratio of a major sixth. This lies between 1 and 2, so we can add it to the table. Time to pile on our next fifth. To calculate the string ratio needed to produce the interval which leads to the note E, we need to take the ratio of the previous note of A and multiply it by the ratio of a pure fifth, which is 3/2. This gives us an interval fraction of 81/32. This is where we run into another problem. All of our string ratios need to lie in between the unison and the octave, and therefore in between the numbers 1 and 2. When we convert the improper fraction into a mixed number, we get 2 and 17/32, which is obviously greater than 2. This is because we started at the fundamental of C. The first pure fifth took us to G. The second pure fifth has taken us to D, which we moved down an octave. Our next fifth took us to A, and then when we piled another fifth on top of that, it took us to E, but in the second octave. To bring the note E down an octave, so its ratio lies in between 1 and 2, we need to divide by 2. This gives us a final interval fraction of 81/64, which is a ratio of 81 to 64. This is the interval ratio needed to produce a major third. We will use all of these interval ratios later on in the video to create every mode which Pythagoras would have used. Let's add this to the table. Time to pile on our next fifth. To calculate the string ratio needed to produce the interval which leads to the note B, we need to take the ratio of the previous note of E and multiply it by the ratio of a pure fifth, which is 3/2. This gives us an interval fraction of 243/128, which lies between 1 and 2, so we can add it to the table. This is also the interval fraction of a major seventh. And it's time to pile on our final fifth. To calculate the string ratio needed to produce the interval which leads to the note F sharp, we need to take the ratio of the previous note of B and multiply it by the ratio of a pure fifth, which is 3/2. This gives us an interval fraction of 729/256. Now this gives us the same problem as we've had before. All of our string ratios need to lie in between the unison and the octave, and therefore in between the numbers 1 and 2. When we convert the improper fraction into a mixed number, we get 2 and 217/256, which is obviously greater than 2. This is due to the note ending up in the second octave, just like we saw with the notes D and E, which we moved down an octave. To bring the note F sharp down an octave so its ratio lies in between 1 and 2, we need to divide by 2. This gives us a final interval fraction of 729/512. This is the interval ratio needed to produce an augmented fourth. This is a vital interval which we will need to calculate the fourth note in the Lydian scale, which has a fundamental note of F and a fourth note of B. Let's add this to the table. OK, it's time to calculate the intervals required to produce the notes on the left. But first, would you agree with me if I said we can find the interval which will produce the note F in two ways? Either going left by the interval of a pure fifth or right by an interval of a pure fourth. And we can find the note B flat by going left by the interval of another pure fifth or going right by another interval of a pure fourth. Can you see that if we use the interval of a fourth, both of our next notes F and B flat will lie in the octave where we need them to be? Therefore, we are going to use the pure fourth ratio which Pythagoras discovered when plucking 3/4 of the length of a string. This also keeps the notes in the octave where we need them to be. And if we did continue to use the 3/2 fraction of a pure fifth for the intervals going left, we would need to invert it and use the fraction 2/3. You may wish to use this fraction when calculating your ratio, so I'm going to show you just one example to prove no matter which method you use, you will always arrive at the same answer. So here is the alternative method. To calculate the note of F moving left, we need to take the ratio of the note C, which is 1, and multiply it by 2/3, which is the inverse of the pure fifth fraction. Obviously, this will give us a fraction ratio of 2/3, which is less than 1. This means that the note F is out of range, as it is placed in the octave below where it needs to be. Therefore, we need to multiply by 2, which gives us the fraction 4/3, or the ratio 4/3. Exactly the same as the interval of a pure fourth. Let's add the ratio of a pure fourth to our table. So now let's get on with our calculations. Time to pile on our next fifth, or fourth as the case may be. To calculate the string ratio needed to produce the interval which leads to the note B flat, we need to take the ratio of the previous note of F and multiply it by the ratio of a pure fourth, which is 4/3. This gives us an interval fraction of 16/9, which lies between 1 and 2, so we can add it to the table. This is the interval ratio of a minor seventh. Time to pile on our next pure fourth, which we remember is equivalent to a fifth if we were moving left. To calculate the string ratio needed to produce the interval which leads to the note E flat, we need to take the ratio of the previous note of B flat and multiply it by the ratio of a pure fourth, which is 4/3. This gives us an interval fraction of 64/27, which is the same as 2 and 10/27. This shows the note has ended up in the next octave, as we have now moved in fourths from C to F to B flat and now to E flat. We have seen this a few times before now, so we know the drill. Let's divide by 2 to bring the ratio down into the required octave, giving us a final interval fraction of 32/27. This is the interval ratio of a minor third. Let's add it to the table. Time to pile on our next pure fourth, which again is equivalent to the fifth if we were moving left. To calculate the string ratio needed to produce the interval which leads to the note A flat, we need to take the ratio of the previous note of E flat and multiply it by the ratio of a pure fourth, which is 4/3. This gives us an interval fraction of 128/81, which lies between 1 and 2. This is the interval ratio of a minor sixth. Let's add it to the table. Time to pile on our next fourth, which we remember is equivalent to a fifth if we were moving left. To calculate the string ratio needed to produce the interval which leads to the note D flat, we need to take the ratio of the previous note of A flat and multiply it by the ratio of a pure fourth, which is 4/3. This gives us an interval fraction of 512/243, which is the same as 2 and 26/243. This shows the note has ended up in the next octave, so let's divide by 2 to bring the ratio down into the required octave, giving us a final interval fraction of 256 over 243. This is the interval ratio of a minor second. Let's add it to the table. Time to pile on our final fourth, which we remember is equivalent to a fifth if we were moving left. To calculate the string ratio needed to produce the interval which leads to the note G flat, we need to take the ratio of the previous note of D flat and multiply it by the ratio of a pure fourth, which is 4 over 3. This gives us an interval fraction of 1024 over 729, which is the interval ratio of a diminished fifth. This is between 1 and 2, so let's add it to the table. So let's take a closer look. Now we have all the interval ratios which Pythagoras calculated to produce all the notes on the diatonic scale of C, or the equivalent of this, which is the Ionian mode. Oh no, hang on, I've just spotted something. Aren't F sharp and G flat the same note? But the interval ratios we have calculated are different, meaning they can't be the same note. Let me check this again. Yes, they're definitely the same note. So we have calculated the interval ratio of G flat as 1024 over 729, and the interval ratio of F sharp to be 729 over 512. This means the ratio of G flat is 1.405, and the ratio of F sharp is 1.425. What's happened? This means that F sharp is slightly sharper than G flat. Oops! Okay, I have an idea. If we work out the ratio of these values and the number is greater than 1, which is equivalent to unison, then we can definitely tell that F sharp is sharper than G flat. To find the ratio of F sharp to G flat, we need to divide the ratio of F sharp by the ratio of G flat. So that's 729 over 512 divided by 1024 over 729. This gives us 531,441 divided by 524,288, which equals 1.01364. This looks way too complicated. Let's make it easier. Earlier we worked out the value of the interval ratio of F sharp to be 1.425 and the value of the ratio of G flat to be 1.405. This also gives us 1.01364. This is the value of the Pythagorean comma. The Pythagorean comma comes about because when we pile pure fifths on top of each other around in the circle of fifths, the final fifth actually shoots past the pitch of G flat, making F sharp slightly sharper than G flat. 1.01364 is the numerical value of the Pythagorean comma, the measurement of a tiny interval produced when F sharp shoots past G flat. I will explain more about this in detail shortly. Musical intervals are measured in cents to precisely quantify the distance between two pitches. In our current system, which is different to the Pythagorean system, 100 cents is the measurement of one semitone. When we work out the number of cents in the tiny interval produced when F sharp shoots past G flat, in other words, the measurement of the Pythagorean comma, the value is 23.46 cents, or the equivalent of what we now know to be just over a quarter of a semitone. This means the start of the circle and the end of the circle don't meet. Imagine we have gathered together the order of fifths back into a circle, travelling from G flat all the way around the circle back to F sharp. Due to the size of the interval of a pure fifth, F sharp arrives back to G flat, but slightly further along than where we started, like this. And as we have heard, this extra little interval is called the Pythagorean comma. The reason for this is because Pythagoras' interval of a pure fifth is too big, and therefore we don't end up exactly where we started from. If we use Pythagoras' pure fifth interval ratio of 3 to 2, we shoot past where we started. Therefore, we have to make the final fifth interval slightly smaller to pull F sharp back to equal the pitch of G flat, so the circle can start again, like this. This smaller interval has a ratio of 262,144 to 177,147 and is called the Wolf interval. So therefore, the reason why this Pythagorean comma existed is because Pythagoras' pure fifth interval was actually too big. It meant that one interval had to be made smaller in order to close the circle of fifths. Nowadays we have 700 cents and a perfect fifth interval. This is why the circle of fifths we use works perfectly. Pythagoras' pure fifth actually contains very close to 702 cents. This is why when we arrive at the enharmonic change of F sharp and G flat, F sharp is sharper than G flat as it shoots past. Depending on which note he started, one fifth interval had to be smaller than every other fifth interval to ensure he could start the next octave on the correctly pitched note. As you can imagine, if all intervals between the fifths are 702 cents and the final interval is less than 702 cents, that last interval isn't going to sound very nice, which is why it is known as the wolf interval. So let's have a go at calculating the wolf interval. We are going to calculate the size of the wolf interval in cents between the notes of B and G flat. If you remember, we have to make the size of this interval smaller as we approach F sharp, so the swap between F sharp and G flat can happen at the identical pitch. The size of the wolf interval is the same size as Pythagoras' pure fifth interval of 702 cents, minus the extra little bit called the Pythagorean comma, so we can pull back the F sharp which shoots past G flat. As we know, the measurement of the Pythagorean comma is 23.46 cents, which we will subtract from 702 cents, which is the size of Pythagoras' pure fifth interval, making the wolf interval measure 678.54 cents. Let's round it up to one decimal place, which is 678.5 cents. Let's add it to the circle. This interval is called a diminished sixth as it goes from B to G flat and is flatter than a pure fifth. No wonder it has been given the name the wolf interval. A perfect fifth today measures 700 cents, and with the wolf interval measuring 678.5 cents, it must sound excruciatingly awful. Now I know what you're thinking. If Pythagoras didn't use the note G flat, why does it matter if the interval from B to G flat sounds like a wolf howling? That would be a good question. And the problem raised here doesn't affect music until many years later when it moved away from the use of modes to the use of tonality. However, what did affect the sound of the music were the individual notes produced using the repetitive pure fifths method that we have seen so far in this video. When compared to modern tonality and the use of equal temperament, many of the notes on Pythagoras' scale are sharp or flat, due to the interval between the fifths being 702 cents instead of 700. Let's compare the resulting pitches from the ratios produced from Pythagorean tuning when compared with modern-day tuning in equal temperament. We'll do this using a C major scale or the Ionian mode. The first C and the last C are in tune. The second and third notes created from a major second and major third interval are both sharp. Using the pure fourth interval makes the note flat. And finally, the pure fifth, the major sixth and the major seventh make the resulting note sharp. So even if the notes were only used for melodic purposes, each note of the melody, except the tonic and the octave, would be out of tune when compared to the tuning we use in the present day. As you can see, when starting on the tonic of C, the keys containing flats would be flatter than modern day pitching, and keys containing sharps would be sharper than modern day pitching. Also, we must remember that Pythagorean tuning was still being used at the beginning of the Renaissance period in the 1300s, approximately 1800 years after Pythagoras died. Pythagorean tuning was eventually replaced by mean tone tuning during the Renaissance period, and there were obvious reasons for this. By the Renaissance period, harmonic aspects of music were created in which two or more voices would sing their own melodic line at the same time. This often involved using the intervals of pure fourths and fifths together, as this created the most pleasing sound within the Pythagorean tuning. However, eventually composers wanted to branch out from creating music made up of mainly pure fourths and fifths, and start to utilise major thirds and major sixths in their music, which they were unable to do satisfactorily due to the Pythagorean tuning. For example, if composers created a two-part harmony in C major using the notes C with E, or F with A, in other words, in major thirds, or these notes within a triad, due to the Pythagorean major third interval being nearly 8 cents wider and therefore sharper than the modern day equal temperament major third, it made the music sound dissonant, rather than the pleasant mellow sound we have come to expect from the major third and major sixth intervals. Imagine creating a piece of music where one part was playing an F and one part playing an A. The F would be flat and the A would be sharp. Ouch! The placement of the wolf interval around the key of F sharp became an issue, because the note F sharp eventually became one of the most used accidentals along with B flat. Moving the placement of the wolf interval between the keys of E flat and G sharp became best practice, as it effectively hides the highly dissonant interval among the least frequently used chromatic accidentals in medieval and early Renaissance music. Let's have a go at moving the wolf interval between the keys of E flat and G sharp, because we know moving round to the right makes the interval sharper and sharper. If we want to hide the wolf interval between G sharp and E flat, then G sharp is going to be 23.46 cents larger than it needs to be, and we will be moving around to the right to reach it. This means we need to change the key of D flat to its enharmonic key of C sharp. Let's also add the key of G sharp by A flat. Now let's add the key of D sharp by E flat. So, to hide the wolf fifth in between G sharp and E flat, we are effectively pulling the D sharp back, which ended up sharp due to the size of the interval created by the 3:2 ratio, to equal the pitch of E flat, like we did earlier when our circle tried to close with F sharp and G flat. The wolf interval will now appear between the notes of G sharp and E flat. Apparently, due to the wolf interval eventually causing such a problem, in order to fix the fault in the tuning, some Renaissance organ makers would use split keys, allowing the organist to have a key for D sharp and a separate one for E flat. The back half of the key would play D sharp, tuned to the sharp end of the fifth chain, and the front half would play E flat, tuned to the flat end. This would enable them to avoid the wolf fifth entirely. Just as an aside, when Pythagorean tuning was adapted in the Renaissance period to mean tone tuning, the major third interval was prioritised instead of the pure fourths and fifths of Pythagorean tuning. Each of the fifth intervals was reduced just enough to bring the interval of a major third to a pure 386 cents. However, this worsened the wolf interval to make it howl even more. But this was overcome by placing the wolf interval in between G sharp and E flat, notes which rarely followed each other in Renaissance music. Let's find the interval ratios which will produce our new sharp notes. We need to find the interval ratios which will produce the notes of C sharp, G sharp and D sharp. Remember, we are now moving right on our circle all the way round to D sharp, and we are only moving left until we reach E flat. We are presuming that D sharp is going to be sharper than E flat, due to the Pythagorean comma. But let's see what happens when we finish the calculations. To calculate the string ratio which will produce the note of C sharp, we need to take the ratio of the previous note of F sharp and multiply it by the ratio of a pure fifth, which is 3/2. This gives us an interval fraction of 2187 over 1024, which is greater than 2. This shows the note has ended up in the next octave, so let's divide by 2 to bring the ratio down into the required octave, giving us a final interval fraction of 2187 over 2048. To calculate the string ratio which will produce the note of G sharp, we need to take the ratio of the previous note of C sharp and multiply it by the ratio of a pure fifth, which is 3/2. This gives us an interval fraction of 6561 over 4096, which lies between 1 and 2, so let's add it to the table. To calculate the string ratio which will produce the note of D sharp, we need to take the ratio of the previous note of G sharp and multiply it by the ratio of a pure fifth, which is 3/2. This gives us an interval fraction of 19,683 over 16,384, which lies between 1 and 2, so let's add it to the table. Do you remember that F sharp and G flat turned out to be different pitch notes? And now we find that D sharp and E flat are different pitch notes too. Let's see if D sharp to E flat is exactly the same value of sharpness like when we compared F sharp with G flat by calculating the ratio. If it's exactly the same value of sharpness, then when we work out the ratio, the answer will be the value of the comma. The value of the comma when we calculated the ratio of F sharp and G flat was 1.01364. Let's calculate the ratio of D sharp and E flat and see if the value of the comma is the same. D sharp had an interval ratio of 19,683 over 16,384, which equals 1.2013549804685. And the interval ratio of E flat was 32 over 27, which equals 1.185185185185. Therefore, the ratio of D sharp to E flat is 1.2013549804685 over 1.185185185185185, which gives us a value of 1.013643264770508. which when rounded to 5 decimal places is 1.01364, which is the exact value of the comma. In fact, you'll also find that the ratio of C sharp to D flat is also 1.01364, as is the ratio of G sharp to A flat. In fact, for all pairs of enharmonic equivalent notes, the sharp note will always be the same value of sharpness when compared to its equivalent flat note. So now he had finished calculating his interval ratios, let's find out how he used them. And this is the best bit and what all the hard work has been for. Pythagoras had worked out the string interval ratio required to produce every single note of every mode based in the key of C major. We looked at the Ionian mode earlier, so let's move on to the Dorian mode. As you can see, this mode makes use of the minor third and minor seventh intervals to produce the notes F and C. The Phrygian mode makes use of the minor second and minor sixth intervals to produce the notes F and C. The Lydian mode makes use of the augmented fourth interval to produce the note B. The Mixolydian mode makes use of the major and pure intervals, along with the minor seventh to produce the note F. The Aeolian mode, which is also the relative natural minor scale of C major, unsurprisingly makes use of the minor third, minor sixth and minor seventh intervals to produce the notes C, F and G. The final mode, called the Locrian mode, makes use of the minor second and augmented fourth intervals to produce the notes C and F. Do you think Pythagoras knew about the failings of his system? We know that a pure interval of a fifth is 701.955 cents, or as Pythagoras knew it, a ratio of 3 to 2. And Pythagoras piled pure fifth onto pure fifth to calculate the string interval ratio needed to produce each of the notes on the circle of fifths, like this. When we add up all of these fifths or multiply 701.955 cents by 12, we reach 8,423.46. Do you recognise the numbers in red here? 23.46. Yes, it's the number of cents in the Pythagorean comma. From this we can work out that we must need 8,400 cents for the circle to close, making a total of 700 cents for each interval. This was exactly what was solved with a new tuning system called equal temperament, which is the tuning system we use in the present day. But what I don't understand is, being a master mathematician, Pythagoras would have worked this out for himself. I mean, not the number of cents, but the idea of the comma. Have a look at this.
But you knew about the comma, didn't you, Mr. Pythagoras?
It's quite easy to work out that Pythagoras knew about the comma because he discovered the following information himself. The ratio of a pure fifth is 3 to 2. The ratio of an octave is 2 to 1. When we go from the lowest C on the piano to the highest C on the piano, we cover a range of 12 fifths. When we go from the lowest C on the piano to the highest C on the piano, we also cover a range of 7 octaves. This means if we work out the cumulative ratio for the 12 fifths and compare it with the cumulative ratio of the 7 octaves, we should land on exactly the same pitch for that last C. This would have been an easy calculation for Pythagoras to make, even though he didn't have a piano. Let's try it. There are 7 octaves on a piano. Pythagoras found out that the ratio of an octave is 2 to 1. We need to raise the first octave 7 times to find out the ratio of the highest octave. The calculation for this is 2 to the power of 7. In other words, 2 times 2 times 2 times 2 times 2 times 2 times 2, which gives the answer 128. There are 12 fifths on a piano. Pythagoras found out that the ratio of a fifth is 3 to 2. We need to raise the first fifth 12 times to find out the ratio of the highest fifth. The calculation for this is 3 over 2 to the power of 12. In other words, 1.5 times 1.5 times 1.5 times 1.5, etc., which gives us the answer 129.746. Oh dear. Moving up 7 octaves gives us a value of 128. Moving up 12 fifths gives us a value of 129.746. It seems Pythagoras' calculations have gone a little crazy, as these should be exactly the same value. Surely Pythagoras would have known that 7 octaves is the same as 12 fifths. Let's calculate the ratio of the 12 fifths to 7 octaves to see the difference. So here we have the calculation of 12 fifths to 7 octaves, which is 129.746 to 128, which is equal to 129.746 over 128, which gives us the answer 1.013640625. I recognise this from somewhere. I know, it's the same as 23.46 cents, which is exactly the same value as the Pythagorean comma. We knew it, and here's Pythagoras admitting to it. So if Pythagoras knew about the comma and all the problems it would cause, why didn't he alter his system? Equal temperament made each fifth equal in order to close the circle of fifths. This altered the size of the fifth to 700 cents instead of 701.955 cents, and this is what we call a perfect fifth today. But why are we still left wondering why Pythagoras, this master mathematician, didn't make this change himself? Apparently, Pythagoras had a love of pure rational ratios, and trying to alter the fifths to accommodate such tiny changes would have spoilt his system. Pythagoras and the Greeks believed that musical intervals should be based on simple integer ratios. The pure fifth was considered sacred. If you change the tuning slightly to fit the pure fifths into octaves, you lose the pure 3 to 2 ratio. Pythagoras refused to break the mathematical perfection of individual intervals for the sake of the overall scale. He didn't think there was a flaw in his tuning. Instead, the creation of the wolf fifth was just a little quirk of his tuning. Plus, the wolf fifth, which was the only real issue with Pythagoras' system, was considered to affect only remote keys when placed in the harmonic system, and that it wouldn't have really stopped music functioning. At the time, music was mostly monophonic, a single melody line, so instrumentalists could alter this themselves. Music did not modulate between different keys at the time when Pythagoras was alive, so a perfect 12-tone scale was not as important as keeping individual common intervals in pure tune. Although Pythagoras did not invent the circle of fifths as a functional musical tool, he is fundamentally responsible for the mathematical discovery that makes it possible. But just think, this happened over 2,500 years ago, and we are still using the circle of fifths, albeit in an altered form, but we are still using it. Pythagoras wasn't terribly bothered that the development of his system didn't work perfectly in a musical sense, provided his ratios were made up of whole numbers. I think we can finish by saying that Pythagoras was certainly a pioneer and foundational figure in music theory, and thoroughly deserved his title, Father of the Science of Music.